Welcome back, guys. Let's see how we can solve another question from the chapter 4 of the engineering mechanics by Meriam. And for this gripping force P that is applying on the handles of this tool, we need to determine the normal force exerted on the small round stock by each jaw of the compound pliers. So talking about this stock, and at the end the question is asking us to state any assumptions that we are taking. So first of all, we are in equilibrium, so we're gonna assume that we are in equilibrium, and we're gonna use the equilibrium equations that we have. Sum of all forces in x equals 0, same for the y, and we're gonna have one moment equations as well. We need to dismantle this system or these pliers in order to find the unknowns in here. So we can start with this part at first, and after that we're gonna move on the second member where we have this part, and based on that we can find the unknowns that we have in here. So another assumption that we need to take is that we're gonna assume that all the forces are perpendicular, and this little angle that we have in here, we're gonna assume that this angle is also perpendicular. So if we just call this normal force that the question is asking, so this is going to be perpendicular as well. And since we have pins in here, so technically for pins, we consider both X and Y components, but in here, if we just want to consider X component, we won't be able to solve the question because we have too many unknowns. So we're going to consider that we only have a vertical component at each of these points. So for D, for example, we're just going to consider one vertical component. We're going to call it D. And we're going to have the same thing for C. We're just going to have one single component in Y direction. Let's just call our X and Y in here too. And now we can move on. So we're going to start with the right side because that's where we can find the relationship of P. And we're going to be interested in C because C is going to be in both members. So if you consider this direction in here, it's going to be in this direction in the other member. And also we're going to have another component at A. So from the blue part, we're going to find the relationship between C and P. So for doing that, it makes sense to do the moment about point D counterclockwise positive. So that way we can get rid of the force at D, which is something that you're not interested in. So let's see what we have. We're going to have the moment of P about D, which is going to be a clockwise moment. So negative P times the distance from the vertical distance from D to the line of action. So this distance, which is 5.5 inches. And we're going to have the moment of the C counterclockwise. So it's going to be positive C. The distance is going to be 2.5 equals 0. So our C in here is going to be 5.5 divided by 2.5 P. Now that we have this, we know on the second member, we're going to have the same thing, 5.5 over 2.5 P. And now if we just do the moment about point A, again, counterclockwise positive, we're going to get rid of the A, and we can find the relationship between N and P, which is basically what the question is asking. So the moment of N is going to be clockwise, so negative N times the distance would be 3.5 inches. So we have it here, 3.5. And the moment of C about A is going to be in this direction, so counterclockwise positive. We can just put the value of C, what we found the previous step. And our distance would be, again, the vertical distance from A to the line of action of the C, which is going to be 1. And this will be also equal to 0, again, because of our equilibrium assumption. And yeah, that's going to give us the relationship between N and P. So our n would be basically 5.5 over 2.5 times 3.5 p, and let's see what we get. So 5.5 divided by 2.5 times 3.5, and our n is going to be 0.629 p, and this is going to be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.